Hello everyone. Have you ever wondered what exactly is light? Is it just something that helps us see, or does it carry hidden secrets about the universe? Today, we'll travel back to the late 19th century, a golden age of physics, when scientists were unlocking the mysteries of electricity, magnetism, and light. James Clerk Maxwell, one of the greatest physicists ever, came up with four beautiful equations that unified electricity and magnetism into a single theory, electromagnetism. He predicted that oscillating electric and magnetic fields can travel through space as waves, and their speed, a stunning 3 times 10 to the power 8 meters per second, exactly the speed of light. That's when it struck the world. Light itself is an electromagnetic wave. Soon after, Heinrich Hertz put this to the test in 1887. He generated and detected electromagnetic waves in the lab, confirming Maxwell's predictions. Light was now seen as a wave that could reflect, refract, interfere, and diffract, just like ripples on water. However, nature had more surprises waiting. Around the same period, scientists began exploring what happens when electricity passes through gases at very low pressures, using a device called a discharge tube. When the air pressure inside the tube was reduced to about 0.001 millimeters of mercury, something fascinating happened. A faint glow appeared on the glass wall opposite the cathode, the negatively charged electrode. Its color changed depending on the glass, yellowish-green for soda glass, bluish for others. What caused this mysterious glow? It seemed to come from rays emitted by the cathode, and thus they were called cathode rays. This was the first clue that electricity could behave very strangely when passed through near empty space. Enter Sir J. Thomson, a brilliant experimental physicist who decided to solve this puzzle. He used crossed electric and magnetic fields to carefully measure how cathode rays deflect and found something astonishing. By analyzing their motion, he calculated their charge-to-mass ratio, E by m, as 1.76 times 10 to the power 11 coulombs per kilogram. Even more amazing, this ratio was the same no matter what gas filled the tube or which metal formed the cathode. That meant the particles inside every atom were identical, universal in nature. Thomson concluded these cathode ray particles were tiny, negatively charged constituents of all matter, and he named them electrons. Now that the electron was discovered, the next big question was, how much charge does it actually carry? To find out, Robert Millikan in 1913 performed one of the most elegant experiments ever, the oil drop experiment. He sprayed tiny oil droplets into a chamber and observed them through a microscope. By applying a controlled electric field between two metal plates, he could make the charged droplets float, rise, or fall, almost magically suspended in midair. By balancing gravitational pull and electric force, he calculated the charge on each droplet. And he found that all measured charges were multiples of a smallest unit, 1.602 times 10 to the power minus 19 coulombs. This proved that electric charge is quantized. Once you know E and E by m, finding the electron's mass is simple physics. Let's calculate it together. Mass equals charge divided by charge to mass ratio. That is, m equals open bracket 1.602 times 10 to the power minus 19 close bracket divided by open bracket 1.76 times 10 to the power 11 close bracket. Pause. Solving that gives approximately 9.1 times 10 to the power minus 31 kilograms, an unimaginably small mass. This means an electron is about 1/1836 the mass of a hydrogen atom, practically weightless on an atomic scale. So tiny, yet it carries the fundamental unit of negative charge. By the turn of the 20th century, physics had entered a new era. With the discoveries of electrons, X-rays by Roentgen, and radioactivity by Becquerel and the Curies, scientists realized that atoms weren't indivisible, they had structure. These breakthroughs laid the foundation of modern atomic physics. They opened the doors to new models of the atom, from Thomson's plum pudding to Rutherford's nuclear model and Bohr's quantized orbits. It was like peeling layers of an onion. Every discovery revealed a deeper level of nature's design. Let's quickly wrap up what we've learned. We began with Maxwell's electromagnetic waves and Hertz's experiments confirming the wave nature of light. Then, through gas discharge and cathode ray experiments, J. Thomson discovered the electron. Finally, Millikan measured its charge, proving that electric charge is quantized. These discoveries revealed that matter and radiation are deeply connected, both showing dual behavior as waves and particles. It marked the dawn of quantum physics, a revolution that reshaped our understanding of the universe.